Hi. In the 5th century before Christ, Zeno formulated several paradoxes to demonstrate the impossibility of motion. The most famous of these is known as the Achilles and the Tortoise paradox. Let us imagine a race between a crippled Achilles and the Formula One Tortoise, to whom Achilles still grants a certain advantage. To set the stage, suppose the track is 1 kilometer long, Achilles runs at 1 kilometer per hour and the tortoise at half kilometer per hour. Suppose also that Achilles grants the tortoise a 500 meters head start. When the race begins, Achilles needs to catch up with the tortoise. To do so, he must cover the 500 meters head start. In the time it takes Achilles to run this half of kilometer, the tortoise will cover half of the distance, so 1/4 of kilometer. Then Achilles must cover this 1/4 of kilometer, during which the tortoise will advance by 1/8 of kilometer, and so on ad infinitum. From this, Zeno concludes that Achilles will never catch up with the tortoise. Now, it is clear that there is something peculiar about this reasoning, because after 1 hour, both Achilles and the tortoise will reach the final line. How do we explain this paradoxical situation? Well, the ambiguity in Zeno's reasoning lies in the calculation of time. In fact, Achilles takes half an hour to cover the first half of kilometer, a 1/4 of hour for the next 1/4 of kilometer, making a total of 3/4 of hour for the first 2 segments. Then he takes 1/8 of hour for the next 1/8 of kilometer, resulting in a total of 7/8 of hour for the first 3 segments, and so on. The total time is then the sum of all these times. But what is this sum? Now, we can observe that if we take the sum of the first n terms, so 1/2 plus 1/4 plus 1/8 and so on, plus 1/2 to the n, this sum is easily equal to 1 minus 1/2 to the n, or if you want, 2 to the n minus 1/2 to the n. So we see that when n gets big, this quantity, which is always less than 1, approaches 1. Therefore, if there is a reasonable value for the total time, this should be equal to 1, exactly as expected. So the point is that the sum of an infinite number of times does not result in an infinite time. Historically, this is one of the first examples of what we call an infinite sum of numbers, or a series. This example also guides us in providing a general definition. So let n be a sequence of real numbers, and we want to define the total sum of this sequence. We could start by calculating some partial sums, like S0 equal A0, S1 equal A0 plus A1, S2 equal A0 plus A1 plus A2, and so on. Sn in general is the sum of the first n plus 1 element of this list. Now, the idea is that to define the total sum of this number, we do the limit of partial sums taking n to plus infinity. Formally, we say that the series is convergent if the limit of partial sums exists and it is finite. We say that the series is divergent if the limit exists, but it is infinite. And finally, we say that the series is indeterminate when the limit of partial sum does not exist. In the case of a convergent series, the limit of partial sums defines also the sum of the series. Now, let's see this definition in an important example, the geometric series. This refers to the sum of the powers of a real number q, also called the ratio of the series. Let's start by calculating partial sums Sn. Here we notice that if we compute Sn plus 1, this is the sum of the first n plus 2 powers of a q, starting from exponent 0. It can be written as 1 plus q, then times this, which is nothing but Sn. And here we get a first remarkable identity, Sn plus 1 equal 1 plus qSn. On the other hand, writing Sn plus 1 as the first of the sum of the first n plus 1 powers, which is Sn, plus the last power, q to the n plus 1, this yields Sn plus q to n plus 1. By equating these two formulas, we easily get Sn equal this fraction. Of course, this formula requires that q be different from 1, and for q equal 1, we can directly determine the value of the sum, because in this case, when you plug a value q equal 1 into this sum, we get a sum of 1s repeated n plus 1 times. So Sn is equal n plus 1 in this case. So we get this, finally, this formula for the partial sums. With this in hand, we can now discuss the limit of Sn. So we see that for q different from 1, everything depends on this quantity. So we have that this quantity for modulus of q less than 1 goes to 0, and therefore this fraction will go to 1 over 1 minus q. For q greater than 1, q to n plus 1 goes to plus infinity, so this makes numerator going to minus infinity, divided by this, which is negative, goes to plus infinity. And finally, for q less or equal than minus 1, it is easy to see that this term oscillates without any limit, so there is no limit. For q equal 1, the situation is much easier because the sum is n plus 1 that goes to plus infinity. In summary, we can say that the geometric series is convergent when the ratio is in absolute value less than 1, and this is the sum of the series. It is divergent when the ratio is greater or equal than 1, and indeterminate when q is less or equal than minus 1. Well, that's it. Now, what are the next steps for you? Well, first of all, try to practice with the definition. Here you have a few examples on which you can try to see what happens checking convergence for these sums. And if you want to something more spicy, you could consider this problem. For example, you start from this remarkable formula for the sum of the geometric series, you square it, and you try to find out this relation here. Good luck.